Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. The cosmos holds many secrets, but perhaps none as perplexing as the invisible forces that shape our universe. As humans, we're accustomed to understanding our world through what we can see, touch, and measure. Yet surprisingly, everything we've ever observed, from the smallest bacterium to the largest galaxy cluster, represents just 5% of what exists. The remaining 95%? A cosmic enigma divided into two mysterious components, dark matter and dark energy. These two forces, despite their similar names, are fundamentally different phenomena with distinct properties and effects on our universe. Their existence reveals a humbling truth. Despite centuries of astronomical advancement, we've barely scratched the surface of understanding what our universe is actually made of. Dark matter makes up approximately 27% of the universe. Unlike ordinary matter, it doesn't interact with the electromagnetic force, making it invisible to telescopes. We can't see it, but we can detect its gravitational influence on visible matter. Think of it as an invisible scaffold holding galaxies, together preventing stars from flying apart as they spin. Dark energy, comprising roughly 68% of the cosmos, presents an even greater mystery. Rather than pulling things together like gravity, dark energy pushes things apart, accelerating the expansion of the universe. This revelation, discovered in 1998, shocked the scientific community and earned the Nobel Prize in Physics in 2011. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The discovery of these dark components revolutionized our understanding of cosmology. For decades, scientists assumed the universe's expansion would gradually slow due to gravity. Instead, observations of distant supernovae revealed the expansion is accelerating, a finding so counterintuitive that astronomers initially doubted their measurements. To appreciate the difference between dark matter and dark energy, imagine a cosmic tug-of-war. Dark matter works with gravity, pulling matter together to form cosmic structures like galaxies and clusters. Dark energy works against gravity, driving these structures farther apart over cosmic timescales. Both remained hidden from human knowledge for most of scientific history. The first evidence for dark matter emerged in the 1930s when Swiss astronomer Fritz Zwicky observed galaxies in the Coma cluster moving faster than their visible mass should allow. He proposed Dunkelmaterie, dark matter, as the missing mass holding these galaxies together. Initially dismissed, his hypothesis gained traction in the 1970s when Vera Rubin and Kent Ford observed similar anomalies in the rotation of spiral galaxies. Dark energy remained completely unknown until the late 20th century. Its discovery required precision measurements of the most energetic explosions in the universe, type Ia supernovae, serving as standard candles to measure cosmic distances. Two independent research teams, the Supernova Cosmology Project and the High Z Supernova Search Team, found that distant supernova appeared dimmer than expected, indicating the universe's expansion was accelerating rather than slowing down. These discoveries fundamentally altered our cosmic perspective. The universe is not only stranger than we imagine, it's stranger than we can imagine. As we journey through the following segments, we'll explore these cosmic mysteries in depth, examining the evidence for their existence, the ongoing search to understand their nature, and what these dark components reveal about the past and future of our universe. Dark matter remains one of the most compelling mysteries in modern astronomy. Unlike the ordinary matter that makes up stars, planets, and people, dark matter doesn't interact with light or other forms of electromagnetic radiation. It's completely invisible, passing through both ordinary matter and itself like ghostly tendrils, detectable only through its gravitational effects. The evidence for dark matter's existence is extensive and compelling. Galaxy rotation curves, measurements of how stars orbit the centers of their galaxies, reveal that outer stars move much faster than they should, based on the visible mass alone. Without some additional unseen mass, these galaxies would tear, themselves apart. Similarly, gravitational lensing, the bending of light around massive objects, indicates the presence of more mass than what we can see. The movement of galaxies within clusters, the large-scale structure of the cosmos, and the patterns in the cosmic microwave background radiation all point to dark matter's existence. When scientists map dark matter's distribution using these gravitational effects, they find it forms a vast cosmic web. This dark matter scaffold provided the architectural framework for the visible universe. In the early cosmos, dark matter clumped together first, creating gravitational wells that attracted ordinary matter, allowing the first stars and galaxies to form. Without dark matter, the universe would look radically different, perhaps lacking galaxies altogether. What exactly is dark matter made of? The leading theory suggests it consists of an undiscovered fundamental particle, something beyond the standard model of particle physics. These hypothetical particles, known as WIMPs, weakly interacting massive particles, would have mass but interact with ordinary matter only through gravity and the weak nuclear force. Numerous experiments worldwide are hunting for these elusive particles. Deep underground laboratories shield ultra-sensitive detectors from cosmic radiation, hoping to catch the rare moment when a dark matter particle interacts with ordinary matter. Facilities like Xenon at Gran Sasso in Italy, LUX Zeppelin in South Dakota, and Pandex in China use tanks of liquid xenon as their detection medium. When a dark matter particle collides with a xenon nucleus, it should produce a tiny flash of light and freed electrons that scientists can detect. Particle accelerators like the Large Hadron Collider at CERN take a different approach, attempting to create dark matter particles through high-energy collisions. If successful, these particles would escape the detectors unseen, but scientists could infer their creation from missing energy in the collision aftermath. Astronomical observations continue to refine our understanding of dark matter's distribution and behavior. The Hubble Space Telescope and more recently the James Webb Space Telescope have observed gravitational lensing effects that allow scientists to map dark matter around galaxy clusters. Meanwhile, the Dark Energy Survey has created the largest maps yet of the cosmic web structure. Alternative theories do exist. Modified Newtonian dynamics, MOND, suggests that gravity behaves differently at galactic scales, potentially eliminating the need for dark matter. However, observations of colliding galaxy clusters, particularly the Bullet Cluster, strongly favor dark matter's existence. In these cosmic collisions, the visible matter interacts and slows down, while the dark matter components pass through each other unimpeded, creating a separation between the visible mass and the gravitational center, a smoking gun for dark matter. As astronomical instruments become more precise and particle detectors more sensitive, scientists edge closer to identifying the true nature of this invisible cosmic scaffold. The discovery of dark matter particles would not only solve one of astronomy's greatest mysteries, but also open a new chapter in fundamental physics, potentially revealing a hidden sector of particles and forces beyond our current understanding. While dark matter pulls the universe together, dark energy pushes it apart. This mysterious repulsive force permeates all of space, exerting negative pressure that counteracts gravity and drives the accelerating expansion of the cosmos. Every cubic centimeter of seemingly empty space contains a tiny amount of dark energy, an amount so small it's undetectable locally, yet across the vastness of space, its cumulative effect shapes the evolution and ultimate fate of our universe. The discovery of dark energy in 1998 ranks among the most revolutionary findings in modern physics. Two independent teams, led by Saul Perlmutter on one side and Brian Schmidt and Adam Rees on the other, were measuring distant Type Ia supernovae to determine how much the universe's expansion was slowing down due to gravity. Type Ia supernovae serve as excellent standard candles because they always reach approximately the same peak brightness, allowing astronomers to calculate their distances with remarkable precision. What these researchers found defied all expectations. The most distant supernovae appeared dimmer than they should have been if the universe's expansion were slowing down. The only explanation was that the expansion was actually accelerating, with galaxies flying apart at an ever-increasing rate. This revelation was so surprising that many scientists initially doubted the findings, but subsequent observations, including data from the cosmic microwave background, baryon acoustic oscillations, and galaxy clustering, have repeatedly confirmed the universe's accelerating expansion. The simplest explanation for dark energy is Einstein's cosmological constant, a term he originally introduced to his equations of general relativity to create a static universe, then famously rejected as his greatest blunder when Edwin Hubble discovered the universe was expanding. In modern physics, this cosmological constant is often associated with vacuum energy, the baseline energy of empty space itself, arising from quantum fluctuations. However, theoretical calculations of vacuum energy yield values approximately 120 orders of magnitude larger than astronomical observations suggest. This discrepancy, called the cosmological constant problem, represents one of the most severe disconnects between quantum mechanics and general relativity. Alternative explanations include quintessence, a dynamic energy field that varies across time and space, and modifications to Einstein's theory of gravity itself. Some scientists even question whether dark energy exists at all, suggesting that our understanding of gravity at cosmic scales might be fundamentally flawed. What makes dark energy particularly challenging to study is that, unlike dark matter, it doesn't clump together. It spreads uniformly throughout space, leaving few distinctive signatures for astronomers to detect. The primary evidence comes from mapping the universe's expansion history using various distance markers and observing how cosmic structures have evolved over billions of years. Several major scientific initiatives have been designed specifically to investigate dark energy. The Dark Energy Survey used a specially designed 570-megapixel camera mounted on the Victor M. Blanco telescope in Chile to map hundreds of millions of galaxies, detect thousands of supernovae, and observe patterns of cosmic structure. NASA's Nancy Grace Roman Space Telescope, planned for launch in the mid-2020s, will conduct an even more extensive survey, providing unprecedented insight into dark energy's properties. The European Space Agency's Euclid mission, launched in 2023, is mapping the three-dimensional distribution of up to 2 billion galaxies across one-third of the sky, measuring how dark energy has influenced the universe's structure throughout cosmic history. What makes dark energy particularly consequential is its long-term implications. If dark energy continues to dominate the cosmos as it does today, the universe's expansion will continue accelerating forever. Distant galaxies will eventually recede faster than light due to the expansion of space itself, not violating Einstein's cosmic speed limit, disappearing from view. In the extremely distant future, trillions of years from now, even neighboring galaxies will become unreachable, leaving each galaxy an isolated island in an increasingly vast and empty cosmos. Detecting something invisible presents formidable challenges for scientists. Yet through ingenious experimental designs and observations, researchers have developed multiple approaches to study both dark matter and dark energy, proving that what can't be seen directly can still be measured and understood. For dark matter, astronomers employ several detection strategies. Indirect detection methods observe how dark matter's gravitational influence affects visible objects. Galaxy rotation curves, measurements of orbital velocities at different distances from galactic centers, consistently show stars moving faster than the visible mass would allow, suggesting an invisible mass component providing additional gravitational pull. The motion of galaxies within clusters similarly indicates more mass than meets the eye. Gravitational lensing provides perhaps the most visually striking evidence. According to Einstein's general relativity, mass warps spacetime, bending light paths. When light from distant galaxies passes through massive galaxy clusters, it bends around invisible dark matter concentrations, creating distorted images. By mapping these distortions, astronomers can create detailed maps of dark matter distribution. The technique has revealed spectacular dark matter structures including the famous bullet cluster, two colliding galaxy clusters where dark matter passed through the collision unimpeded, while visible matter interacted and slowed down. Direct detection experiments take a different approach, attempting to catch the rare moments when dark matter particles interact with ordinary matter. Deep underground laboratories house these experiments to shield detectors from cosmic rays that would otherwise overwhelm any dark matter signal. The most sensitive experiments use noble liquids like xenon or argon, cooled to cryogenic temperatures. If a dark matter particle collides with an atomic nucleus in these detection mediums, it should produce tiny flashes of light or liberated electrons that sensitive instruments can detect. Particle colliders like the Large Hadron Collider represent a third approach, trying to create dark matter particles through high-energy collisions. These particles would escape detection directly, but scientists could infer their creation from missing energy and momentum in collision products. For dark energy, detection methods focus primarily on measuring the universe's expansion history. Type Ia supernovae serve as standard candles, cosmic explosions with known brightness that allow astronomers to calculate distances precisely. By comparing redshifts, which indicate recession velocities, with distances determined from these supernovae, scientists can track how cosmic expansion has changed over time. Baryon acoustic oscillations, BAOs, offer another powerful technique. These are periodic fluctuations in the density of visible matter, echoes from sound waves that propagated through the early universe. The characteristic size of these fluctuations serves as a standard ruler that allows astronomers to measure how cosmic distances have evolved over billions of years. The cosmic microwave background, CMB, radiation left over from approximately 380,000 years after the Big Bang, contains subtle patterns that encode information about the universe's composition and expansion history. Missions like the Planck satellite have mapped these patterns with extraordinary precision, providing key constraints on dark energy properties. Large-scale galaxy surveys complement these approaches by mapping the three-dimensional distribution of matter across cosmic time. Projects like the Dark Energy Survey, the upcoming Vera C. Rubin Observatory's Legacy Survey of Space and Time, and the Nancy Grace Roman Space Telescope will chart billions of galaxies, allowing scientists to measure how cosmic structures have evolved under dark energy's influence. Computer simulations play a crucial role in interpreting this data. By creating virtual universes with different dark matter and dark energy properties, scientists can predict what various measurement techniques should detect, then compare these predictions with actual observations to constrain the properties of these mysterious components. Despite these sophisticated techniques, both dark matter and dark energy continue to guard their secrets. No dark matter particle has been conclusively detected in laboratory experiments, and the fundamental nature of dark energy remains elusive. Yet with each technological advancement and observational campaign, scientists draw closer to understanding these enigmatic cosmic forces. While the existence of dark matter and dark energy has become the scientific consensus, not all researchers are convinced these mysterious components actually exist. Some propose that what we interpret as evidence for dark substances might instead indicate flaws in our understanding of gravitational physics itself. These alternative theories present radical revisions to fundamental physical laws rather than adding invisible components to the universe. For dark matter, the leading alternative is modified Newtonian dynamics, MOND, first proposed by Israeli physicist Mordechai Milgram in 1983. MOND suggests that Newton's laws of gravity require modification at the extremely low accelerations, typical of galactic scales. According to this theory, gravity behaves differently than expected over very large distances, becoming stronger than Newton's inverse square law would predict. This modification could explain galactic rotation curves without invoking dark matter. While MOND successfully predicts the behavior of individual galaxies with remarkable accuracy, often outperforming dark matter models, it struggles to explain observations of galaxy clusters and gravitational lensing. Proponents have extended the theory into relativistic versions like TVES, tensor vector scalar gravity, to address these shortcomings, but challenges remain, particularly in explaining the cosmic microwave background radiation patterns and the behavior of colliding galaxy clusters like the Bullet Cluster. For dark energy, alternatives include modified gravity theories that attempt to explain cosmic acceleration without introducing new energy components. One approach, called FR gravity, modifies Einstein's field equations by replacing the Ricci scalar r with a function of r. Another proposal, the Dvali-Gabadadze-Porati (DGP) model, suggests our universe exists on a four-dimensional brane within a five-dimensional bulk spacetime, with gravity leaking into the extra dimension at large scales, creating the illusion of cosmic acceleration. Other researchers explore whether inhomogeneities in the universe's structure might create the appearance of acceleration when viewed from our particular cosmic location. These void models propose we live near the center of an enormous cosmic underdensity, with the apparent acceleration resulting from how light travels through this non-uniform space. Quantum approaches to dark energy include various scalar field theories. Quintessence models propose a dynamical field similar to the Higgs field, but operating at cosmic scales. Unlike Einstein's cosmological constant, quintessence can vary across space and time, potentially explaining why dark energy's effects became dominant only in the relatively recent cosmic past. A related concept, phantom energy, suggests dark energy might actually strengthen over time, potentially leading to a Big Rip scenario where the universe's expansion becomes so violent that it tears apart galaxies, stars, planets, and ultimately, atoms themselves. Some theorists propose connections between dark matter and dark energy through unified dark fluid models. These suggest a single exotic substance might behave like dark matter on small scales, clumping around galaxies, while acting like dark energy on cosmic scales, driving acceleration. Quantum gravity theories, attempts to reconcile general relativity with quantum mechanics, offer additional possibilities. Loop quantum cosmology suggests the universe undergoes cycles of expansion and contraction with what appears to be dark energy, potentially relating to quantum gravitational effects. String theory provides numerous dark energy candidates, including brane interactions and the vast landscape of possible vacuum energy states. Perhaps the most provocative alternative comes from theoretical physicist Eric Verlinde, who proposes that gravity itself might not be a fundamental force but rather an emergent phenomenon, similar to how temperature emerges from the collective behavior of particles. In his theory of entropic gravity, what we interpret as dark matter and dark energy might be manifestations of information and entropy at cosmic scales, while the standard lambda CDM model, featuring dark energy as a cosmological constant and cold dark matter, remains the leading paradigm due to its remarkable success explaining diverse observations. These alternative theories continue to stimulate research, driving observers and theorists to devise new tests that might distinguish between competing explanations for our accelerating, dark matter-filled universe. The dance between dark matter and dark energy has shaped our universe's evolution, from its earliest moments to the present day, and will determine its ultimate fate. Understanding this cosmic ballet provides insight into where we came from, where we are and where we're heading on the grandest possible scale. In the beginning, dark matter played the leading role. After the Big Bang, as the primordial plasma of elementary particles cooled, dark matter began clumping together under its own gravity, forming a vast cosmic web. This dark scaffolding created the gravitational seeds that would eventually grow into the galaxies and galaxy clusters we see today. Ordinary matter, unlike dark matter, could interact with radiation, creating pressure that resisted gravitational collapse. Only after the universe cooled sufficiently, approximately 380,000 years after the Big Bang, could normal matter break free from radiation and fall into the gravitational wells created by dark matter. This process created the first stars and galaxies, which formed preferentially along dark matter filaments, explaining the cosmic web structure we observe today. For billions of years, gravity, enhanced by dark matter, dominated cosmic evolution, gradually pulling matter together into increasingly complex structures. Computer simulations show that without dark matter, galaxies as we know them simply couldn't have formed within the universe's lifetime. Our very existence depends on dark matter's invisible influence. Dark energy remained relatively insignificant during these early epochs. While present since the beginning, according to the standard cosmological model, its density remained constant, while matter density decreased as space expanded. Approximately 7 billion years after the Big Bang, the declining matter density finally fell below dark energy density. At this pivotal moment, dark energy began dominating the cosmic expansion, and the universe's growth started accelerating. We live now in this dark, energy-dominated era. Every day, the accelerating expansion carries distant galaxies farther away from us at an ever-increasing rate. Fortunately, this acceleration is only noticeable over vast distances and timescales. Our solar system, galaxy, and even our local galaxy group remain safely bound together by gravity. The evidence for this acceleration appears in multiple independent observations: the dimming of distant Type Ia supernovae, the precise patterns in the cosmic microwave background radiation mapped by satellites like WMAP and Planck, the distribution of galaxies across space measured by surveys like SDSS and DES, and the subtle patterns of baryon acoustic oscillations detected in the cosmic web. Looking toward the cosmic future, dark energy's dominance will only increase. If dark energy maintains its current properties, consistent with Einstein's cosmological constant, the universe will continue expanding forever. With the acceleration becoming more pronounced, galaxies outside our local group will eventually recede faster than light, not violating Einstein's theory, as this happens because space itself expands, making them permanently unreachable and eventually invisible to future astronomers. In approximately 100 billion years, all galaxies beyond our local group will have disappeared beyond our cosmic horizon. The Milky Way will have merged with Andromeda and nearby satellite galaxies to form one enormous elliptical galaxy sometimes called Milkomeda. Future astronomers born in this isolated island universe would have no observational evidence for the Big Bang, cosmic expansion, or most of the universe we can currently observe. A sobering thought about the limits of knowledge. More exotic forms of dark energy could lead to different fates. If dark energy strengthens over time, the phantom energy scenario, the expansion could become so violent that it eventually overcomes all other forces, ripping apart galaxies, stars, planets, and ultimately atoms themselves in a big rip. Alternatively, if dark energy weakens or reverses sign, the universe could eventually stop expanding and recollapse in a big crunch. Some theories even suggest connections between dark energy and the multiverse hypothesis. In eternal inflation models, our universe might be just one bubble in a vast multiverse, with different regions exhibiting different dark energy values. This could provide an anthropic explanation for dark energy's puzzlingly small value. In regions with stronger dark energy, galaxies couldn't form and life couldn't exist to observe them. Understanding dark matter and dark energy thus provides more than abstract knowledge. It reveals our cosmic origin story, explains our present circumstances, and foretells our universe's ultimate destiny. As we venture deeper into the 21st century, the quest to understand dark matter and dark energy stands at the frontier of physics and astronomy. The next decade promises transformative discoveries through new experiments, observatories, and theoretical breakthroughs that may finally illuminate these cosmic shadows. For dark matter, a multi-pronged detection strategy continues. Next-generation direct detection experiments are achieving unprecedented sensitivity. Projects like Xenon-T and Lux-Zeppelin use multi-ton liquid xenon detectors with backgrounds so low they can potentially detect just a handful of dark matter interactions per year. Meanwhile, the Darwin Project aims to build the ultimate dark matter detector, a 40-ton xenon observatory sensitive enough to either discover dark matter particles or reach the neutrino floor, where neutrino interactions become an irreducible background. Particle colliders offer complementary approaches. The high luminosity upgrade to the Large Hadron Collider will significantly increase its ability to produce and potentially detect dark matter particles. Future proposed colliders, like the Circular Electron-Positron Collider in China or the Future Circular Collider at CERN, could reach energies high enough to create heavier dark matter candidates beyond the reach of current experiments. Astronomical dark matter investigations are advancing rapidly. The Vera C. Rubin Observatory, starting operations in Chile in 2025, will conduct the legacy survey of space and time, mapping billions of galaxies with unprecedented precision. Its data will enable the most detailed maps of dark matter distribution ever created through weak gravitational lensing measurements. The Nancy Grace Roman Space Telescope, scheduled for launch in 2026, will further revolutionize our understanding of both dark matter and dark energy. With its wide-field infrared vision, it will survey billions of galaxies, measure thousands of supernovae, and map dark matter distribution with extraordinary clarity, free from atmospheric distortions that limit ground-based telescopes. For dark energy research, these same observatories will measure cosmic expansion with unprecedented precision. The Dark Energy Spectroscopic Instrument, DSI, is already creating the largest three-dimensional map of the universe, measuring the precise positions of tens of millions of galaxies to track how cosmic structure evolved under dark energy's influence. The European Space Agency's Euclid mission, launched in 2023, focuses specifically on dark energy, mapping 2 billion galaxies across 1/3 of the sky. By precisely measuring both the shapes of galaxies for gravitational lensing and their three-dimensional distribution for clustering statistics, Euclid will constrain dark energy properties with remarkable precision. Theoretical advances may prove equally important. Quantum gravity theories, attempts to reconcile general relativity with quantum mechanics, could provide new insights into both dark components. String theory, loop quantum gravity, and causal set theory each offer different perspectives on how space, time, matter, and energy fundamentally interconnect at the deepest levels. Machine learning and artificial intelligence are revolutionizing how astronomers analyze the vast datasets these new observatories produce. These computational techniques can identify subtle patterns in cosmic structure that might otherwise remain hidden, potentially revealing new clues about dark matter and dark energy. Multi-messenger astronomy, combining observations across different messengers like electromagnetic radiation, gravitational waves, neutrinos, and cosmic rays, offers another promising frontier. The detection of gravitational waves from neutron-star collisions, combined with their electromagnetic counterparts, has already provided new tests of dark energy theories by measuring cosmic expansion in entirely new ways. Perhaps most exciting are the potential discoveries we can't yet anticipate. Throughout scientific history, major breakthroughs have often come from unexpected directions. New particles, forces, or fundamental principles may await discovery, potentially unifying our understanding of dark matter and dark energy, or replacing them with even more profound insights into cosmic reality. What makes this quest so compelling is how it connects the largest scales imaginable, the entire observable universe spanning billions of light years, with the smallest scales of subatomic particles and quantum fields. Understanding dark matter. And dark energy requires bridging these extremes, potentially revealing deep connections between cosmology and particle physics. As we stand gazing into this cosmic darkness, we're reminded of how science progresses, not from absolute certainty to absolute certainty, but through progressively better approximations of reality. Today's frontier questions become tomorrow's textbook knowledge, and the mysteries that confound us now may inspire future generations of scientists to see the cosmos with new eyes. In this endless quest for understanding, the darkness itself illuminates the path forward.